In 1927, physicists discovered something strange in the double-slit experiment. They fired electrons at a barrier with two openings. On the wall behind, an interference pattern appeared, as if each electron had passed through both slits at once. So they placed a detector to find out which slit each electron actually used. The pattern vanished immediately. The moment they looked, the electron chose. When they didn't look, it didn't. The universe follows different physical rules depending on whether it's being observed. And that sentence is not a metaphor. Let's build this carefully. The double-slit experiment is one of the most important experiments in the history of science, and it's important to understand exactly what it shows and what it doesn't show. You fire a stream of electrons at a barrier that has two narrow slits in it. Behind the barrier is a detection screen. If electrons were ordinary particles, tiny bullets, you'd expect two bands of hits on the screen, one behind each slit. That's what you'd get with actual bullets. Instead, you get something else entirely. Alternating bands of hits and empty space spread across the screen in a wave-like pattern. This is an interference pattern, the signature of waves, not particles. Light does this. Waves in water do this. Two waves spreading out from the same source cancel each other in some places and reinforce each other in others, producing exactly this kind of alternating pattern. But electrons are particles. They hit the screen at single points. Each electron leaves a single dot. And yet, if you fire enough of them, those single dots accumulate into the interference pattern. Each electron, individually, is interfering with itself. As if each single electron passes through both slits simultaneously, and the two paths interfere with each other before the electron hits the screen. This is the wave-particle duality at the heart of quantum mechanics. The electron doesn't behave like a particle traveling one definite path. It behaves like a wave spreading through space, passing through both slits, interfering with itself. And then, when it hits the screen, it collapses to a single point and registers as a particle. Now, you want to know which slit it went through? Reasonable question. You place a detector near one of the slits, any kind of detector, as long as it can tell you which slit the electron used. Here's what happens. The interference pattern disappears. Not slightly reduced, gone. The electrons now hit the screen in two bands, exactly where you'd expect particles to go. The moment you measure which slit, the electron stops behaving like a wave and starts behaving like a particle. This is not a measurement disturbance problem. You might think, the detector is physically interacting with the electron, nudging it, disturbing its path. That's not what's happening. You can design detectors that are as gentle as physically possible. Detectors that barely interact with the electron at all. The pattern still disappears. The crucial variable isn't the physical disturbance. It's whether the information about which slit was used exists anywhere in the universe. If the information exists, if any physical record of which slit was used is created anywhere, the interference pattern vanishes. If the information is erased before you can read it, the pattern comes back. Let that land. It's not about the physical disturbance to the electron. It's about whether the information exists. The universe seems to be sensitive to the existence of knowledge about a particle's path. This is what the observer effect really means. Not that human consciousness collapses the wave function. That's a common misunderstanding. Observation in quantum mechanics means any physical interaction that creates a record of a quantum system's state. It could be a detector, a photon bouncing off the electron, a molecule registering its position. Any physical entanglement with the environment that makes which path information available, even in principle. The electron's behavior changes not because a conscious being is watching, but because its state becomes correlated with something else in the physical world. But here's where it gets stranger. There is an experiment called the delayed choice quantum eraser. In this experiment, after an electron has already passed through the slits and hit the detection screen, You can choose whether to erase the which path information or keep it. And the interference pattern on the screen correlates with your choice, even though the electron already hit the screen before you made it. The future choice of whether to measure or erase appears to influence the past behavior of the electron. This is not time travel. No information travels backward in time. The correlations work out in a way that is statistically consistent, and you can't use this to send signals to the past. But the mathematical fact remains. Whether an interference pattern exists on the already recorded data depends on a choice made after the electron already registered. The timeline is, electron hits screen, you choose, the pattern either appears or doesn't in the already recorded data. Causality, as you normally think about it, is deeply strange in quantum mechanics. Now let's talk about what observation collapses the wave function actually means physically, because this is where interpretations of quantum mechanics diverge, and where honest physicists will tell you we still don't know. The standard Copenhagen interpretation says, before measurement, the electron has no definite position or path. It exists in a superposition, a mathematical combination of all possible states. The wave function describes the probability of finding it in each state if you look. When you look, the wave function collapses to one definite state. Before measurement, asking, which slit did the electron go through, is not a question with a hidden answer. It genuinely doesn't go through either slit in particular. It goes through both in superposition. The many worlds interpretation says, the wave function never collapses. When you make a measurement, the universe splits. There is a branch where you find the electron went through the left slit, and a branch where you find it went through the right slit. Both branches are equally real. The apparent collapse is just your experience of becoming correlated with one branch. In this picture, there are no observers collapsing anything, only branching universes. The decoherence interpretation says, the apparent collapse isn't a physical event, it's a practical one. When the electron interacts with the detector, with billions of particles, it becomes entangled with a huge number of degrees of freedom in the environment. The quantum interference between different outcomes gets scrambled by all those interactions. The different possibilities stop interfering with each other because the information about which path was taken has leaked into the environment in countless tiny ways. From any local perspective, this looks exactly like collapse. The wave function hasn't collapsed. It's just that the off-diagonal terms in the density matrix, the terms that represent the quantum correlations between different outcomes, have become negligibly small. Here's the honest position. All three of these are mathematically consistent with every experiment ever performed. They make identical predictions. We cannot currently distinguish between them by any measurement. The question of what really happens when you observe a quantum system is not settled physics. It is live, contested, and unresolved. This should be uncomfortable. Quantum mechanics is the most precisely tested theory in the history of science. It predicts experimental results to 11 decimal places. Every electronic device you own depends on it. And yet the question of what it means, what is actually happening when a quantum system is measured, is one the smartest physicists alive actively disagree about. Let me give you Feynman's version of why the double-slit experiment is so important. He said it contains the only mystery of quantum mechanics, by which he meant, if you really understand the double-slit experiment, truly, deeply understand it, you understand everything that is strange about quantum mechanics. All of the other quantum strangeness is the same strangeness, dressed in different clothes. The strangeness is this. A particle's history is not determined until something records it. Before recording, all possible histories are real in some sense. They contribute to the probabilities of outcomes. This is Feynman's path integral formulation of quantum mechanics. Every particle takes every possible path simultaneously, and the paths interfere with each other. The path integral is a sum over all possible histories, weighted by the probability amplitude of each history. The result gives you the correct probability of where the particle ends up. It works. It's the right mathematics. And it says that unobserved particles have no single definite history. This has philosophical consequences that are hard to avoid. The moon exists when you're not looking at it, but only because the moon is constantly being observed by photons and air molecules and the gravitational field in an irreversible, thermodynamically one-way process that maintains classical behavior. Large objects decohere. Their quantum superpositions collapse into effectively classical states almost instantaneously because of constant interaction with their environment. You don't have to worry about whether the moon is in a superposition of positions. The decoherence timescale for a moon-sized object is unimaginably short. But electrons, photons, atoms, molecules, small isolated systems shielded from their environment, these are quantum. Their behavior depends on whether they've been observed. They exist in superpositions. They interfere with themselves. And the interference pattern is real, measurable, reproducible, the most precise physical prediction we know how to make. There is a version of this that gets misused constantly. The observer effect proves consciousness creates reality. No, the observer effect says that physical measurement, any physical interaction that creates a record, affects quantum systems. A detector in a vacuum with no human nearby collapses the wave function just as effectively as a human watching. What matters is the physical interaction and the resulting entanglement, not the presence of consciousness. But there is a version that remains genuinely strange even after you correct that misunderstanding. The physical fact is, before measurement, the electron has no definite state. This is not a statement about our ignorance. It's not that the electron secretly went through one slit, but we don't know which. Bell's theorem and the experiments it inspired show that no hidden variable theory, no theory in which particles have definite states that we just don't know, can produce the predictions that quantum mechanics produces. The electron genuinely has no definite path before measurement. The universe is, at the quantum level, genuinely indefinite until a measurement pins it down. And measurement means any physical interaction that creates a lasting correlation between the quantum system and something else in the world. The universe monitors itself through physical interaction. Every detection event, every entanglement with the environment, every irreversible correlation. These are the moments at which quantum indefiniteness resolves into classical definiteness. Let me give you one more image. Schrödinger's cat, you know it. A cat in a box connected to a quantum process, a radioactive atom, that will trigger a poison if it decays. Before you open the box, the atom is in superposition. If the superposition is real, the cat is in superposition too, simultaneously alive and dead. When you open the box, you find the cat definitely alive or definitely dead. Schrödinger invented this not to argue that cats are in superpositions. He invented it as a reductio ad absurdum. He was trying to show that the Copenhagen interpretation had a problem. Quantum superposition can't just apply to electrons and stop applying at the scale of cats. Either superposition is real all the way up, or something physically distinguishes the quantum from the classical. That question, the measurement problem, is still open. Decoherence explains why you never observe macroscopic superpositions in practice, because the decoherence time is negligible. But whether superposition is ontologically real at the macroscopic scale is the question the interpretations disagree about, and no experiment has settled it. Here's what I think matters most about all of this. Quantum mechanics forces a question that classical physics never had to ask. What is the relationship between physical reality and physical information? In classical physics, reality is what it is, regardless of whether anyone knows about it. In quantum mechanics, the existence of information about a system's state changes how that system behaves. Not because knowledge is magical, but because the physical processes by which information is created are the same physical processes that resolve quantum indefiniteness. Observation is a physical act. Measurement is a physical act. And those physical acts have physical consequences. The universe doesn't care whether a conscious being is watching, but it does care, in a physically precise, mathematically defined, experimentally verified sense, whether its state is correlated with anything else. That's what observation means in quantum mechanics. That's what the double-slit experiment is showing. And that is genuinely, profoundly not a metaphor. There's one more layer I want to add, because it connects the observer effect to something you experience every day, and the connection is exact, not metaphorical. Every digital device you own works because of quantum mechanics. The transistor, the fundamental component of every chip in every computer, phone, and electronic device, works by exploiting quantum mechanical effects in semiconductors. The way electrons tunnel through thin barriers, the way energy bands form in crystalline materials, the way doping changes conductivity. All of this is quantum mechanics applied to solid-state materials, and specifically the tunnel diode, the flash memory in your phone, the MRI machine in any hospital. These devices explicitly exploit quantum tunneling, which is the same wave-like behavior that produces the interference pattern in the double-slit experiment. An electron passing through a classically forbidden barrier. A thing that classical mechanics says is impossible, happening constantly and reliably, because the electron doesn't have a definite position until something measures it. The question, does the universe behave differently when nobody is looking, is not just philosophical. It has engineering applications. The answer is yes, and we build hardware that depends on that yes. Here's the deepest version of the question, not, does the universe behave differently when unobserved? We know the answer to that, experimentally. The deep question is, what is it about measurement that makes the difference? What physically distinguishes an observation from a non-observation? When exactly does superposition resolve? Is it when the quantum system touches a large environment? Is it when information becomes thermodynamically irreversible? Is it when consciousness processes the result? We don't know. The interpretations disagree. The experiments don't discriminate between them. And there is something I find important about sitting with that honestly. Quantum mechanics has been tested for a century. It has never been wrong. It predicts the structure of atoms, the properties of materials, the behavior of light, the operation of every electronic device that has ever been built. It is the most precise scientific theory humanity has produced. And at its foundation is a question we cannot answer. What exactly is observation, and what exactly does it do to the physical world? That's not a failure. That's where physics actually lives, at the boundary between what we can calculate precisely and what we cannot yet understand completely. The calculation works. The understanding isn't finished. And the boundary between those two things is one of the most interesting places in all of science. The electron went through both slits. You looked, and it went through one. That's not a metaphor. That's what happened. If something shifted, if the double-slit experiment looks different now, or if the question, what is observation, feels stranger than it did before, leave a comment. Which part landed hardest? That the interference pattern disappears not because of physical disturbance, but because information exists. That the delayed choice experiment puts causality under pressure. That we have the most precise theory in physics and still don't agree on what it means. Or just the specific image of an electron passing through both slits simultaneously, interfering with itself, making the most quantum thing in the world visible as a pattern on a wall. And if you want to keep following questions that don't have settled answers, subscribe. That's what this channel is for.